Hello everyone, my name is Gramuglia. I'm from the Advanced Control System Lab of Virginia Tech, and I will present the paper called A Hybrid Model Reference Adaptive Control System for Multi-Rotor UAVs. To give a little bit of background and motivation for this work, last mile delivery using multi-rotor UAV is being investigated by multiple stakeholders such as Amazon or Walmart or UPS. And inherent challenges lie in the poor characterization of the payload, in the fact that the payload is shifting and moving around, and in the impacts that happen among the payload and the casing in which the payload is placed. The objective is to design an adaptive control system for multi-rotor UAVs that accounts for vehicles under actuation, tracks a user-defined trajectory, is robust to uncertainties deriving from mass, matrix of inertia, and aerodynamic coefficients, and accounts for the hybrid nature of the system dynamics, such as impacts or sudden changes in the vehicle's inertial properties, etc. Now we show the main elements of model reference adaptive control for hybrid planes. So at the top, we have the trajectory tracking aerodynamics. So E represents the trajectory tracking error, and sigma represents an index that tracks the changes in the system dynamics. So this differential equation is in the classical form of model reference adaptive control, while the bottom one is a difference equation, and it describes the system dynamics when resetting events occurs. And so usually resetting events occurs after impulsive forces act on the system, impulsive events such as the payload hitting the casing. Then at the bottom we have the reference model. Again, the top equation is the classical differential equation for model reference adaptive control, and the bottom one is the difference equation that describes the jumps in the reference trajectory of the reference model when resetting events occurs. We have described what could cause a resetting event, but here is the formal definition. So a resetting event occurs every time that this condition is verified, and the gist of it is that whenever the system is not able to dissipate enough energy, so a certain amount of energy is reached, and this level of energy is greater than another energy level, which is given by the sum of the energies that due to for example, impulsive events, then that's when a resetting event is verified. And so we also have resetting event jump in the reference model, meaning that every time there's a resetting event, there's also a jump in the reference trajectory of the reference model, and the quantity with which the jump is defined follows this formula right here, in which P is the solution of comes from the solution of the algebraic Lyapunov equation shown here. In this work, we make a comparison between the proposed hybrid AMRAC system and other two types of control systems, which are a PID controller for its popularity in commercial off-the-shelf microcontrollers employed by UAVs, and with classical AMRAC for fairness of comparison. In fact, it is important to note that the tuning gains between classical AMRAC and hybrid AMRAC are the same. The only thing that changes is the hybrid architecture. The nominal mission used to tune the controllers consists in having the UAV follow a circular user-defined trajectory with a radius of 3 meters and at an altitude of 1 meter with a constant translational velocity of 0.6 meters per second, and the UAV needs to keep the roll axis tangential to the user-defined trajectory at all times. For what concerns the initial condition, the UAV is at rest at an altitude of 0 meters, and its roll axis is radial to the user-defined trajectory. The following video shows the X-8 copter performing this nominal mission, employing the proposed hybrid AMRAC system. This numerical simulation has been executed in the high-fidelity environment by Chrono. To the best of our knowledge, this is the first known use by Chrono to test controllers for autonomous unmanned aerial vehicles. This is the nominal mission scenario. So the UAV starts with its roll axis radial to the user-defined trajectory and is then able to bring it tangential to the user-defined trajectory. This is the hybrid AMRAC formulation, so we see that the vehicle is able to reach steady state and then converge to the user-defined trajectory. And as you can also see, we also have a casing at the bottom of the landing legs, but since this is the nominal mission scenario, there is no payload inside of it. So a hybrid AMRAC control system, a classical AMRAC control system, and a PID control system have been tuned to produce substantially similar levels of performance in both trajectory tracking error and control effort. Here we show the norm of the trajectory tracking error as a function of time, and we have in black the hybrid AMRAC system, in dashed blue we have classical AMRAC, and in red we have PID. And as we can see, the level of performance is very similar for all of the controllers. Here we show the total thrust required by the UAV as a function of time. Again, the performance are very similar except for the 3 spikes that happen in the PID total thrust, and these are due to the fact that the UAV starts with its roll axis, which is radial to the user-defined trajectory. So in order to bring it tangential to the user-defined trajectory, 3 jumps in the yaw angle user-defined trajectory are given, and we see that PID suffers the most from these jumps. In order to challenge the 3 controllers, the following mission has been devised, in which the UAV needs to follow a stadium-like user-defined trajectory, which can be seen on the right. So the UAV will start and follow a straight line of 7 meters, then perform a sharp U-turn with radius 1 meter, and then again follow a straight line till the end. This happens at an altitude of 1.1 meters with a constant translational velocity of 1.2 meters per second, and the UAV needs to keep its roll axis tangential to the user-defined trajectory at all times. In order to further challenge the controller, after 4 seconds from takeoff, a motor failure happens, and after 7 seconds from takeoff, a payload dropping happens. For further details regarding the specs of motor failure and payload dropping, please have a look at the paper. The next video shows the performance of the hybrid AMRAC system, the classical AMRAC system, and a PID control system, all put side by side. So here is the mission scenario. In the left window we have hybrid AMRAC, in the central window we have classical AMRAC, and in the right window we have PID. We see that hybrid AMRAC is the fastest to converge to the user-defined trajectory, and after motor failures happen, we see that also in this case hybrid AMRAC is still the fastest to converge to the user-defined trajectory, while PID is the one suffering the most from this. And then whenever the payload is dropped, we see that PID is still the one that suffers the most from it, while hybrid AMRAC and classical AMRAC converge back to the user-defined trajectory in a much faster way. In the following, we will be comparing the plots of the trajectory tracking error and the total thrust required by each controller, and it will be apparent how the proposed hybrid AMRAC formulation outperforms the other 2 control systems. Here we show the norm of the trajectory tracking error as a function of time, and as we can see, until the first resetting event, which happens here, the hybrid AMRAC system and classical AMRAC system are on top of each other, and the resetting event helps hybrid AMRAC in preventing it from reaching such a high overshoot as classical MRAC does. And we can also see how the PID control cannot cope with such events such as motor failure and payload dropping, and it takes a long time to recover, while the two MRAC controllers are much faster to recover from this, but still hybrid MRAC outperforms MRAC. Here we show the total thrust required by the motors of the UAV as a function of time, and also in this case we see how whenever a resetting event occurs, like in this case and this case, it helps in reducing the amount of total thrust required of hybrid MRAC in black compared to classical MRAC in dashed blue. For further details, please have a look at the paper, A Hybrid Model Reference Adaptive Control System for Multi-Rotor Unmanned Aerial Vehicles by Gramuglia, Kumar, and Andrea Laflido, published in the proceedings of 2024 AIAA SciTech, or send an email to a.laflido@vt.edu. Thanks for watching.